Saxon Algebra 1, Lesson 97. Let's start out easy. There are two ways to think about angles and what they are. One way is to think about two intersecting lines. And notice I just drew basically an X, and that creates angles, right? And what's even better is it creates matching angles. Those two angles are the same size. These two angles are the same size. They're called vertical angles. Way to think about angles. Another way is to think about two half lines, or rays, if you will, being connected from a point of intersection. So this is two half lines easy to see how, okay, you could take this and put it right in here, right? If you drew a dot there, there's the two half rays. Or it's easy to take this and say, okay, extend those out, and you get the same picture. It's two ways of saying the same thing, so it's nothing to get excited about, but different mathematicians over the ages have conceived of these in different ways. We can stand on the shoulders of all those giants and say, we get it both ways, it's fine. Okay, and I want to make sure it's firmly emblazoned in your mind. If we take two lines and have them intersect at right angles, we get this cool quadrant, Cartesian coordinate plane, one thing we call it, but there's 90 degrees in each quadrant. That's kind of a cool thing to remember whenever we talk about angles. We're going to build on this over the years. And then remember that when it comes to triangles, there are three different ways we can configure the angles within a triangle. They always add up, let's write this, the interior angles of a triangle always add to 180 degrees, right? I think we've talked about that before. And by interior angles, I mean what's going on inside the triangle, nothing to do with this space on the outside. We can talk about those too, we will later. Those are called exterior angles, but interior angles means inside of the triangle. We can have what's called an equiangular triangle. That means the three interior angles are all the same. And they have to be 60 degrees because 180 divided by 3 gives us 60, 60, and 60. Okay. So that's one way we can talk about it. But here's the way we're going to want to talk about it today. One of the angles is a right angle. And by right angle, we mean 90 degrees. Okay? That means these two have to add up to 190. But we're going to talk more about, no, we're going to talk about sides too. I take that back. We're going to talk about with right angles the fact that they have very specific names. Again, this is for a right angle. What we're talking about today is specific to right angle triangles, or right triangles is another way we can say that. These have special names. This is called a side. This is called a side, and by that I mean that part of the triangle and that part of the triangle. Those are called sides. This is always called the hypotenuse. And it's a fancy fancy name for the choppy side of a right triangle, the kitty corner side. I'll tell you what I always envision. I always envision that we started with a rectangular piece of paper, or maybe even a perfect square. Mine looks like it came from a square, but it doesn't have to be. And then we cut that piece of paper on the diagonal from corner to corner, and it creates two right angles. That's what I always imagine. So I always think of the hypotenuse as being the edge that we cut with the scissors. All right, so now we have some language, this side hypotenuse. We're going to take that giant puffy cloud of knowledge around all of this, and let's talk about something historical. Once upon a time, there was a dude who lived in Greece. He lived on an island, actually. It was called Samos. And Italy, but the guy was Greek at the time he was born, and his name was Pythagoras. All right, this is 6th century BC, so the 500 BCs, if I remember how to convert that properly, which, you know, I could be completely wrong. He came up with a really cool idea. And again, let me draw a right triangle, and I'm drawing it purposely with the sides of different lengths to show you that that's not important. What's important is that it must be a right triangle. That is critical. This is a side, we said, this is a side. Those are the straight parts of the paper, if you imagine my piece of paper analogy. And the part that we cut, that's called the hypotenuse. Okay, and what we're going to do is we're going to give these letters. We're going to give the sides the letters A and B. Does it matter which side is A and which side is B? No. What matters, though, is the hypotenuse absolutely must be the letter C. And what Pythagoras pointed out is that if you take the square of the two sides and add them together, that will equal the square of the hypotenuse. What? Don't ask me how he came up with this. I do believe he was playing around with some ideas that went back to the Egyptians in like the 2000 BCs. But Pythagoras gets credit for coming up with this relationship between the sides and the hypotenuse of right triangles. And we can use this formula very nicely to find the lengths of different sides of triangles. Let me show you how we can put it into play. And we're going to use it as a tool in lots of different problems as we go on from here. Given the triangle with the lengths of sides as shown, use Pythagorean theorem to find A. Okay, so here's the picture. Now, John has flipped our triangle, hasn't he? That looks a little weird, but we see that little marker in the corner and we go, perfect. It is a right triangle, even if it's positioned in a weird way, and it's going to get weirder before it gets less weird. So we know that the Pythagorean theorem is going to apply. Now, we've got some information about the length of sides, but we don't have it all. So what we do is go, okay, how could we use this and this to come up with an answer for A? Well, what we have to notice is that that is a side, and this is a side, and this is the hypotenuse. I'm just going to write hype instead of writing it all out. So we know that the sides can be A and B. We'll let that one be A since it's already A. We'll let 4 equal B. And then the hypotenuse has to be this side. So we'll let that equal C. So we're using this formula and these values, and we'll write A squared, that's our mystery side, plus 4 squared, because 4 is equal to B, equals 5 squared. See how I did that? Plugging them in. So simple. The only hard part is making sure that you get the sides where the sides belong. These are the sides. And get the hypotenuse over there on the other side by itself. Again, it doesn't matter which side is which, because you're going to add them together anyway once you square them. All right, now we're ready to solve. Just do some algebra. A squared plus 16 equals 25. We subtract the 16. A squared equals, ready for it, 9. And then we take the square root of both sides, and we get A equals 3. Now, we spent some time quite recently solving little equations that look like what I just did. And we said it's actually positive and negative, didn't we? So technically, I should be thinking of this as positive and negative. But here's the thing. In geometry, we always have a picture to provide our reality. Do you think there's any chance that the length of this side is -3? I don't think negative is an option. So we don't have to mess around with that plus or minus business. We know that the length of side A must be 3 units. It doesn't tell us what they are. But we know it's positive because geometry gives us physical context for our answers, and we're not going to have a triangle with a side of -3. Yay! Okay, let's move on and do some more. All right, example 97.2. I'm going to write this again up here. I like to see you guys rewrite your equation on every page so you have it right in front of you. And the more you write it, the more you memorize it, right? So easy. Okay, find side P. But look what John does to us. Look what Pythagoras does to us. They make this crazy floating triangle. But guess what? We don't care. As long as we see that, we know it's a right triangle, and we know that we can use our Pythagorean theorem to solve for a missing side. The only trick is we just have to orient ourselves to what the sides are. The sides are always on either side of the right angle. So we'll call this one A, and we'll call this one B, and we'll put that in the place of C. We can leave it as P. It's confusing when you have 2 letters, but we're trying to match it to this format. So there's my A, there's my B, there's my C. And make double, triple sure that these are the sides and that's the hypotenuse. Yes, I'm good. So we can write that 4 squared plus 5 squared equals, I'll just leave it as P squared, but we then know that goes in the place of C. All right, 16 plus 25 equals P squared, 41 equals P squared. Take the square root of both sides, and we get P. I'm flipping the order now because I like it this way. I don't have to write negative. I can just write P equals the square root of 41. That is not a very satisfying answer, but if we just think about our perfect squares, we know that 41 is between what? 36 and 49, right? That's 6 squared and that's 7 squared. 41 fits in between 36 and 49. So the length of this is 6 point something, 6 and a fraction. And that makes sense given the 4 and the 5. All right, so that's how we can kind of think about what our answer means. All right, that's the correct answer, 97.3. This time our triangle is still a little wonky. It's kind of floating upside down in this example. K, 5 square root of 61. Okay, we recognize we have a right triangle. We have 2 of the 3 sides. We can use Pythagorean theorem. I feel like this really needs a cloud. All right. So we just, again, have to make sure we get our sides together and our hypotenuse opposite. That can be our A, that can be our B, that can be our C, and then we'll go K squared plus 5 squared equals square root of 61 squared, right? Okay, K squared plus 25 equals, now how does this work? We're taking the square root and we're squaring. Those cancel each other out, so this just becomes 61. Subtract. K squared equals Oh, look what John did for us. He gave us a perfect square. So we get k equals 6. Again, we can disregard negative 6. That is not the length of that side. K equals 6. So the moral of that story is just because you get a creepy number in the picture doesn't mean your answer is going to be creepy. It can turn out nice. Here's an example of nice numbers that turned out with a creepy answer. Here we have just the opposite. So don't let those disgusting numbers put you off. 97.4. Here's another weird floaty. They look to me like triangles in space, right? Like zero gravity. That's why they're floating. We don't care what they do as long as they've got a right angle in them. That's all we need. This doesn't work for non-right triangles. It has to be a right triangle. And there's some kooky pictures in the book on page 407. I don't spend a lot of time looking at those because most students find them incredibly confusing at this point. I want you to see how simple and straightforward the Pythagorean theorem is when you use it before I start dragging you into explanations as to what it means. So I don't care about those pictures right now. Just understand what we're doing here and you'll be fine. 12, 8, and m. All right, side, and hypotenuse. I'm going to work over here this time. So 12 squared plus 8 squared equals m squared. Right? Those are the two sides. Okay. Now this is good practice on our bigger squares. That's 144 plus 64 equals m squared. Let's add these. I'm going to write it underneath. It's going to be 208 equals m squared. We are going to take the square root of both sides. Now, our answer will be m equals the square root of 208, but I'm pretty sure we can break this down. Let's see. I'm going to divide this by 2. That would be what? 104. I'm going to do it by 2. That will be 52. I'm going to do it by 2. That will be 26. And I'm going to do it by 2 and 13. Now I'm prime. I can take out 2 pairs of 2s, and that will leave me just the square root of 13 inside. So I'm going to write m equals 2 times 2 is 4 square root of 13 as my final answer. That's correct. Okay? So we do reduce our roots using this prime factoring technique. Remember, right? For every pair of pigs in the house, we can take 1 pig out of the house. There I took out a 2. There I took out another 2. 2 times 2, that's how I got that 4. And then square root of 13 is a pig left inside. All right, so practice on reducing our roots in this as well. All right. Flipping. Section C is going to introduce one more idea related to this. It's called Pythagorean triples. And the idea here is that there are 3 triangles that are commonly used because their numbers work out nice and even. Let me just show them to you and you'll understand. Here's the littlest one. 3, 4, 5. That will always work out to be true. These are the proportion of these sides, 3, 4, and 5. I think we did it at one point because this is 9 and 16. And you add that together and you get 25. There are 2 more. Again, whose numbers just work out really nicely. And 13. And then here's one more. And my triangles look a lot the same. The point is that they are slightly different proportions. They're not, this is not the same triangle 3 times. That says 17, sorry, that's kind of mushy. Okay, but here's the thing. If you memorize these triangles, this one we call a 3, 4, 5, this one we call a 5, 12, 13, and this one we call an 8, 15, 17. Then you can recognize patterns, and sometimes this will save you some work. Okay, so here's an example of how that might look. John draws us 3 triangles. I'm just going to draw them out. Oh my gosh. That's good. Okay, that looks a little better. These are not necessarily perfectly proportional, but I am drawing them more or less the way John did. Okay, this one is 5, 12, and A. This one is 8, B, and 17. And this one is C, 8, and 10. Okay, so we're supposed to find the missing sides not by calculating it using the Pythagoras theorem, which we could, but we're not supposed to do that in these. We're supposed to use our reference triangles here to just fill in the missing pieces. All right, so John's asking us to memorize these and then know them when we see them. So this one, 5, 12, you can say A equals 13. If we've memorized this. If we haven't, then we just have to calculate it. It's not that big of a deal. This one, 8 and 17, oh, our brain goes, wait, I remember something. There it is, B equals 15. Okay, now we see 8 and 10. Well, now wait a minute. We have one with an 8, but there's no 10 in it. So this triangle doesn't match to this picture. This one's no help. It doesn't have an 8 or a 10. This one doesn't have an 8 or a 10, but it's got a 5 and a 4, and we recognize, wait, if we took this and adjusted it, okay, the 10 is twice as much as the 5 at the hypotenuse, and the 8 is twice the 4, then C must be twice the 3. C must be equal to 6. See how I can infer this triangle from this one? That's another way that these Pythagorean triples are useful, is that we not only understand this triangle, but anything that just multiplies up the sides proportionally, like this one is times 2, then we can use it as well. So these are useful tools. These triangles are useful tools for solving for missing pieces if the triangle happens to be the same proportion. I don't get real excited about having you memorize this. At this point, I'm much more interested in you understanding how to use the formula to solve, because that will always work. And if you memorize a few of the easy ones, well, you know, that's cool. But this is not anything that I consider high priority. This is just nice to know, not need to know. All right, that is the end of lesson 97. Farewell.